Good morning. We have a very thin attendance this morning. When we are going to talk on a very hot topic, CCUS. Would you like to know what is the carbon dioxide concentration today? 428 ppm. And just before the pandemic, it was 410 ppm. So we have added so much of carbon dioxide to the atmosphere, and in 2025 it was total 41.6 gigatons, billion tons of carbon dioxide has been emitted into the atmosphere, and that is precisely the reason for increasing global temperature. And the Paris Agreement of 2015 said that we will not allow the temperature rise to be beyond 1.5 degrees Celsius by the year 2100. However, today's predictions say that it may happen by 2027. In other words, we cannot afford to let carbon dioxide go into the atmosphere. Personally, I have been working in this area, and I always say net zero is not the solution. Although it is a glorious term, net negative is the solution. We have to take carbon dioxide out of the atmosphere or wherever it is generated, capture it, utilize it for converting into chemicals, materials. So carbon should not be a part of a fuel system. That's my personal belief, and I say it loud and clear. So in that context, CCUS is a great idea, and we have 5 experts here. They have different experience, and they come from different organizations. So we have Dr. Yashvardhan Verma, who is from IIT Bombay. Very incidentally, his father-in-law was my colleague. So world is too small. Pragya Ramrakhyani, who is the chief manager of BPCL. Sony Rajan, team manager CCUS business development in Mitsui O.S.K lines. Dr. Thomas Koller, regional hydrogen and CCUS MS APAC. And Pranav Sharma, we are awaiting. He is supposed to be somewhere. So ladies and gentlemen, I will give this floor to the young man, Yashvardhan Verma. Thank you.
Thank you for coming. Dr. Yashvardhan Verma. I am a senior research scientist at the National Center of Excellence in CCUS at IIT Bombay. And I'll be presenting some of the work that we are doing to ensure safe and effective CO2 storage using risk analysis in a potential pilot field that we're looking. So just to give a brief context about CO2 storage in India, in 2021 we came out with this mapping the CO2 storage capacity in different basins in India, and we are looking at different mechanisms such as enhanced oil recovery, enhanced coal bed methane recovery in onshore and offshore saline aquifer, as well as basalt formations. And we figured out that India has a huge capacity for CO2 storage. Before this, we didn't have very quantitative and very certain values about these, but we figured out that in saline aquifers, which is usually the largest sources of CO2 storage capacity, we have almost 300 gigatons. In enhanced oil recovery, we can store about 3.4, and similarly through enhanced coal bed methane recovery. And again, in basalt formation, which is a very new and upcoming research topic and is still very uncertain, we figured out that it's almost 100 to 300 gigatons of storage capacity. So India has a huge potential for CO2 storage, which can help in our net zero emission goals. And we also identified which basins should be the first targets for the major oil and gas operators, and where we have the infrastructure to store CO2 as well as capacity. And we identified some of those high and very high potential sedimentary basins. From one of those, the Cambay Basin had been identified in Gujarat basically as one of the potential basins with high capacity as well as infrastructure. And Gandhar field, which has been producing since 1986, is identified as a potential pilot project for CO2 EOR. So now, why do we need risk assessment for CO2 storage? So this comes from mostly European and USA guidelines, where we say risk management is essential to ensure the safety of CO2 storage. And so the whole process starts with an operator or any company gets a storage license, and then they have to demonstrate through risk assessment and project design whether they are capable of storing and effectively storing CO2 for long periods of time. And then they get a storage permit, where then they can actually start injecting CO2 into the underground. So this process takes a lot of time, and this basically establishes confidence in CO2 storage from the regulators, so which can be DGH in the case of India. And that's why it's very essential to demonstrate that the operator has understood all of the risks that are involved in CO2 storage, and that they're taking measures to mitigate it. So this is kind of CO2 storage complex that we identified in the Gandhar field, where we have the Ankleshwar formation, and we have multiple reservoirs stacked by seals, what we call shale formation, which prevent the movement of CO2 from the reservoir to basically leaking into the surface, and that's what we want. These are some of the characterization work that we have done with the help of DGH as well as the British Geological Survey, where we identified the main reservoir for Gandhar field, and what are the kind of depth ranges, what are the thicknesses, is it a good reservoir or not. And we cover nearly 270 square kilometer of the study area. Again, we did more petrophysical characterization, where we are identifying individual layers between the formation. So it's being divided into different sands. So basically sands and shale are interspersed with each other, and we identify what is the porosity range, the permeability range. And this helps us identify how the CO2 once injected will flow in the reservoirs, and whether it will leak from the top of the reservoir, or maybe it might leak from the side. And we do reservoir simulations to figure that out. We did a fault slip potential analysis, which is basically to understand how much pressure can the reservoir hold, because we inject CO2 at a very high pressure, and sometimes that might actually cause fractures which we don't need, and actually cause induced seismicity at the surface. So we need to prevent those, and to understand that, we do pressure analysis to understand which are the faults which are most likely to slip first. And we identified that around 10 megapascal of injection pressure can be increased in the reservoir before we start seeing any anomalous behavior. Based on this, we established a basic CO2 storage project concept, which is at a very initial stage, where we identify that almost 15 megatons of CO2 storage capacity is present, and we can inject around 0.6 megatons per year for almost 25 years through at least 2 wells in the down dip direction. So based on this project concept, then we identify what are the risks involved in this particular project. So the objective is to identify the relevant risk and basically use a risk matrix approach to create a comprehensive risk register that includes prevention as well as mitigation barriers that might prevent basically all the threats from occurring. And we develop a portfolio of mitigation activities that could contribute to the identification of reduction of the identified risks. So this is the bow tie risk assessment framework that we use, where we identify a top event that might cause, that is a threat to the CO2 storage, and then we identify what are the different kind of risks involved to cause that event, and what are the consequences of that event happening. And I'll show you examples of how it happens with using the example of Gandhar field. So, and again, talking about what are barriers. So barriers are basically can be activities or monitoring or any kind of interventions that we can do, either maybe geological or operational, that might reduce the threats of different activities that are going to hinder our CO2 storage or might lead to CO2 leaking from the reservoir. So the risk assessment process is basically involves a lot of experts from different domains involved in the subsurface, and where they describe what are the kind of risks that we can see. And these risks are not delineated to any one domain. It can start from the surface activities to establishing what kind of risks involved in developing infrastructure facilities, to even to going to the depths when we start injecting. So what kind of issues can be while we are injecting, to even post injection. And there's a group of experts that sits down. We describe each risk, we describe the probability and severity of each risk, and then we put it in a kind of a risk matrix where we identify which are the risks which are the ones we need to look at the most first, and then what are high, low, medium, or low severity, low probability risks that we can maybe look into the future. So we identified these risks and then we move on. So what we did first was we worked this with British Geological Survey as well as IIT Bombay, where we identified a lot of these risks, more than 30 to 35 risks that are present in this particular project that we are looking at in Gandhar field. And these are very specific risks that we look at it. They are not generalized risks. They are risks specific to this project. What are the operational parameters? What are the reservoir look like? And we go into the details of each of these risks. We describe these risks, we describe the probability, severity, and what are the prevention and mitigation barriers that need to be put while we are describing those risks and what might help to prevent those. And these are some examples of all the risks that we look at and what are the kind of, so it can be as technical as what are the kind of, if the CO2 laterally migrates from the reservoir to the extent out of the reservoir, and then what are the issues that can happen, whether that is a big risk if it leaks out of the reservoir or that can be still managed. So we measure all of these risks. We go into much more detail in each of these measures, and then we put it into our bow tie framework. So this is the risk register summary. We describe the different events that are happening. So CO2 might leak from the storage complex through wells. CO2 might leak from the reservoir formation and leak to the surface. There might be reduced storage capacity than we initially planned. There might be reduced injectivity. Sometimes there are a lot of issues while we are injecting CO2. The formation might be blocked due to certain pressures. So there might be reduced injectivity, and that reduces what the initial project concept was. And sometimes if it causes something like an earthquake, it might cause a lack of license to the operator to inject CO2. So all of these risks are identified and put under different top events. And then we identify what are the high risk, medium risk, and low risks in these. So based on this, we create this risk matrix where we identify what are the risks from the risk register and map it to the risk matrix, and we identify what are the different probability and severity of each of these risks. And then we put it into our bow tie framework, where I'm giving an example of a top event where CO2 is leakage from the storage complex. So storage complex, the CO2 might leak laterally or might meet vertically as well from the formation. And we see what are the different threats that might cause that event. So it might be if we don't have a proper characterization of a reservoir, then we might see that the CO2 is leaking from reservoir because we don't know what are the lateral extents. Then CO2 also reacts with the formation to create minerals and becomes a carbonate rocks, and that might reduce the CO2 from injecting even more. There might be leakage from the main seal that we have, the shale layers. So these are all the different threats that are present which can cause CO2 leakage from the storage complex. And on the right hand side, we see what are the different consequences of that happening. So it might lead to contamination of potable water aquifers that are present maybe in the nearby area. CO2 might leak from the reservoir and reach the surface, and then might cause impact to people, might cause impact to ecosystems. It can basically cause environmental impacts, and as well as if there are other hydrocarbon users or operators who are extracting hydrocarbon from the nearby wells, CO2 might leak there, and it might leak from their wells itself, not just our wells. So these are all the consequences of those happening. So we establish these to identify what are the different risks and what is the probability and severity. Not because we are trying to kind of create a negative impact on CO2 storage, but to identify and to basically assure our regulators that we understand what are the risks and we are taking measures to make CO2 storage effective and safe for thousands of years. So I'm just looking at now one event to one consequence and trying to identify what are the different barriers present between that event and between that consequence happening. And we create these barriers between each threat and each event and consequences. So it becomes a very large document that we go into much more detail into, but this is just an example of what are the different barriers that we see. So we see that there is a separation of storage complex from receptors. There might be potable water aquifers, but we have enough separation from those to actually not cause a contamination of water aquifers. Then we have monitoring wells, which actually based on reservoir simulation, we see that the CO2 is moving exactly as we predicted from our simulations. Then if we see CO2 moving a little bit different, we can also have modify our CO2 injection strategy such that CO2, if it's going to leak, it doesn't leak too much. And then there's corrective action where we are already kind of doing monitoring wells and basically we need to give a corrective action plan to our regulators to see what happens in the case of actual leakage. We have these actions in our portfolio that we can enact. So this looks at all of these events and consequences in order to understand and make sure the regulator understands that we understand everything, and we are making sure that all of these consequences and all of these threats become as ineffective as possible, so that these events that we identify don't actually take place, and that will actually help to make our injection strategy as well. Now, what happens after we do the risk assessment? So initially, as we identify from the risk matrix, we have an assessed risk, what is the probability, what is the severity. Then we apply these mitigation as well as preventive barriers, and then we try to see what is the, so there is an initial uncertainty in the consequence, and there is initial uncertainty in probability. So what we are trying to do is reduce the probability and the consequence of these events, but also reduce the uncertainty, so that we know more and more about the subsurface, and we know more with certainty that these events are not going to cause catastrophic failures. So that's what we are trying to do from the whole risk assessment process. We are reducing the probability, severity, as well as reducing the uncertainty. So for a conceptual project, most mitigation measures comprise more kind of reservoir studies, more drilling wells, more doing surveys and characterization, etc. So at these early stages, so right now Gandhar has not started injecting, it's very a very potential field. So we have a lot of pre-feasibility studies going on. So this helps us in defining what kind of studies we need to do right now in order to make sure that Gandhar is a successful CO2 project. So basically from this whole process, we identified the critical risks that are involved, and we identified that there are a lot of old wells, legacy wells as we call them, which we do not understand the whole structure, so they might cause a lot of CO2 leakage, so we need to work on those. And we also don't understand the full extent of the reservoir, so we need to characterize it better. We identified what are the effective barriers like pressure management, monitoring, and so remediation. And of course, there was a very expert input from a very multidisciplinary team who understand a lot of the CCUS chain from the start to end, which helps strengthen the risk rating. And then we use the bow-tie framework to highlight the vulnerabilities and the corrective mitigation measures. And this basically helps us reduce uncertainty and support safe and scalable deployment of CO2 storage in India. Thank you.
The second is Pragya. Your topic is what? Is it there on the screen? No, anyway, please come.
Good morning, everyone. I am Pragya, Chief Manager, Bharat Petroleum Corporation Limited. I will be presenting my work on turning pollution into possibility, that is CO2 derived DME for India's kitchens, and how BPCL IP program is shaping India's transition towards low carbon cooking fuel. So my presentation will cover current LPG scenario in India, Indian government push on dimethyl ether, and joint BPCL IP program on DME technology development, then techno-economic assessment, summary, and way forward for large-scale adoption. So in last 1 decade, uses of LPG has increased rapidly in India. Currently, there are 33 crore active LPG connections, which has more than doubled over the past decade. In the year 2014, it was around 14.5 crores, and thanks to schemes like Pradhan Mantri Ujjwala Yojana and PEHL, Pradhan Mantri Ujjwala Yojana has provided over 10 crore free LPG connections, and PEHL scheme has streamlined the subsidy delivery. So and now the LPG coverage is more than 100% in the country, and today almost every household has access to LPG. So despite this strong growth, India imports 60 to 70% LPG, and 90% is used for household purpose. So with rising demand and increase in and high import dependency, India needs locally produced alternative of LPG for the future. And DME is the next generation green alternative of LPG. It is a clean, colorless, and non-toxic fuel, And if it is produced from renewable sources, it can reduce CO2 emissions up to 80% compared to fossil derived LPG. It burns very clean with zero sulfur, and particulate emissions are minimal. Its physico-chemical properties are similar to LPG, and it enables us to mix with LPG with the existing systems. It can be blended 20 to 30% with LPG in existing systems without major change or any change in the current existing infrastructure. So these advantages make DME a promising fuel for low carbon and net zero energy systems. Overall, we can say that DME is a strong candidate for India's clean energy transition and for reducing import dependence. So this table compares properties of DME with other fuels like diesel and methane, propane, butane. So its cetane number is even higher than diesel, giving it an excellent ignition quality. Its boiling point is minus 25 and density is in the range of LPG. So the existing storage and handling systems can be used for this without any change. Its calorific value is little less compared to LPG and diesel, but it burns clean and no sulfur is there, so it can be used. It is an ideal fuel for blending in LPG. So Indian government is also pushing for use of methanol and its derivative fuels. Government is pushing promoting use of DME through methanol economy program of Niti Aayog, and this program aims to reduce LPG imports, subsidies and emissions by encouraging adoption of methanol based fuels. And under DME LPG blending program, BIS permits up to 20% blending with LPG. The long-term strategy of India is to enhance the energy security by using domestic resources like coal, biomass and captured CO2. And at present there is no plan for complete LPG replacement. It is for blending and pilot projects. So BPCL and IIT has developed an integrated process for making DME from refinery flue gas captured carbon dioxide. So in the process, first step is to capture CO2 from the refinery flue gas, and it is a well established process. Then captured CO2 is compressed at high pressure and fed to the methanol reactor, where it reacts with hydrogen in the presence of methanol catalyst at temperature range of 220 to 60 degrees centigrade, and pressure is around 60 centi bar. In per pass conversion is 15 to 18%, and remaining gas is cycled back to the reactor, and the converted one is sent for methanol separation. The purified methanol is sent to the reactor for dehydration reaction in the presence of aluminum or zeolite catalyst. So methanol gets dehydrated and we get DME of around 98% purity. So the first key step in the process is methanol, CO2 hydrogenation to methanol. So first step is CO2 hydrogenation to methanol. It is an exothermic process, and this slide compares the performance of 5 different catalysts. So here we can see that catalyst 5 gives the best performance. that conversion is around 8.7%, and selective for methanol is 100%, which is of importance for us. And these results are at 200 degree centigrade temperature, 30 bar pressure, and 7200 GHSV. If we further increase the temperature to 230 or 240 degree centigrade and pressure is increased, so this performance will further improve. So our target is to get 15 to 18% conversion of CO2 in this reactor. So the next major step in the integrated process is methanol dehydration to DME. This too is an exothermic process, and materials like alumina, zeolite or clays can be used for dehydration of methanol to DME. We can see that catalyst D, which is an imported one, gives the best performance, that is 93% conversion at 300 degrees centigrade. But catalyst A performance is also very close to catalyst D, and which is of very significance for us because catalyst A is indigenously synthesized, and BPCL and IP, we are working with a catalyst supplier to scale up this formulation. So this gives us confidence to use indigenously developed formulation for large scale production of DME. So the last part of the presentation is techno-economic assessment of the process. For this, we have taken 15 KTPA plant, and two scenarios were considered: gray hydrogen, that is hydrogen we get in refineries from SMR unit, and green hydrogen, that is from produced from electrolyzer. And plant life assumed is 20 years, and yeah. This is a process flow sheet which was used for this analysis. This is completely heat integrated and optimized process. So first section is for CO2 absorption. So this section is for CO2 absorption, and CO2 is fed to the methanol reactor. After this separating methanol from water, this purified methanol is fed to methanol dehydration reactor, from where we get DME as product, and the purity obtained is above 98%. So in the break-even price arrived is 138 rupees for scenario 1, where gray hydrogen is used, and for scenario 2 the price break-even price arrived is 209 rupees per kg, and the major contributor is operating cost, that is raw materials, energy and utilities. So if we better heat integration and optimization may further reduce the prices. And for green DME, definitely as electrolyzer cost will go down and renewables cost will reduce, it will definitely come down. So at present it may look these costs are high, but as time goes, maybe 10 to 15 years, it may be in the range of this fossil derived LPG. And yeah, so to summarize, India imports 60% LPG, and DME offers a clean drop-in fuel for blending up to 20-30%. And this 20% this limit has been decided based on safety and studies done by done in India, in other countries as well. And integrated indigenous process has been developed, which comprises CO2 capture, methanol synthesis, and dehydration of methanol to DME. And the process which we have worked on, it uses captured CO2 from refinery flue gas and gray hydrogen. Pilot plant, we are in the process of establishing or testing pilot plant at BPCL. This is a joint project by BPCL and IIP. Indigenous catalyst and BPCL has designed a multi-tubular reactor for the process. So it enables us to go for the scale up. And techno-economics shows that break-even, that price of DME for grey hydrogen is 138 and grey hydrogen is 209 rupees. So this is a way forward that we have to complete and optimize the pilot plant with our catalyst, and we have to scale up the indigenous catalyst and reactor technology for refinery deployment. And finally, we have to move towards commercial demonstration to reduce LPG imports and emissions. Thank you everyone.
Thank you, Pragya. Our next speaker is from industry, Mr. Sony Rajan, Mitsui O.S.K. lines. So he will talk on marine solution for CCUS. Yeah.
Good morning, everybody. I would like to thank IEW for the opportunity to present marine solutions for CCS. Mitsui O.S.K. Lines, we are a Japanese shipping company. We are the world's second largest and we're the largest LNG ship operator. We operate all type of ships, tankers, LNG, bulk carriers, car carriers and containers. It will be simpler for me to tell you the type of ships we don't operate rather than the type of ships we operate. We are present globally. We have a large presence in India also. In India, we're involved in shipping, logistics, IT systems, ship crew management, real estate, and also a CVC venture of ours. Been in India since 1966. We do a lot of work on ships. We recently signed deals day before yesterday with ONGC and GAIL for the ethane and the LNG ships. Coming to CCS, it was introduced that the net zero framework and a target of 1.5 degrees by 2100. So far, we don't seem to be heading in that direction. A lot of it, especially with the power generation, especially due to data centers. But at least all international agencies agree that CCS is definitely needed towards the decarbonization pathway for hard-to-abate industries. Cross-border CCS, it does add an additional complexity, but India has a huge potential for domestic CCS and CCU pathways. With regard to moving the CO2 from the emitter to the storage, there are multiple options such as truck, rail, pipeline, waterways and sea. And the value that MOL brings is in the last two, that is the water and the sea ways of moving CO2 from emitter to storage. The map on the right was already shown, which shows the major geological formations, but also of relevance is the map on the left, which shows the various large point sources of CO2 emission. So while pilot projects are already ongoing, at some point when we need to scale up, we'll have to move the CO2 from the emitters till the storage points. And that is where primary modes of movement are either pipeline or by shipping in other regions that CCS are being deployed. With regard to the value chain, we have the emissions from the emitter, we have the liquefaction, interim storage, and then we have transportation. I'll focus only on the shipping side. Then we again have interim storage, and then either injection or utilization. I've listed a lot of companies that MOL has been working with on different projects globally, both in Europe and also in APAC region. While I'm based in Tokyo, we do look after projects at the global reach. Right on top, you have the industry and research organizations that MOL is part of, and we've been part of a lot of studies, including with my fellow panelists from DNV, for studies for different ways of moving CO2, different ways of injection using the marine solution. And I'll dwell a little bit into some of these solutions. We have done a fair bit of work since 2021 in different designs of ships and different sizes. We have the small ones, we've done feasibility studies, we have MOUs with different Japanese companies. MOL is part of the committee that is supporting the Japanese policy framework being developed. We are part of the JOGMEC advanced CCS projects. We're involved in the pilot and demonstration projects also being done in Japan. The most recent one is the joint venture which we've established with Petronas. This is towards a ship-owning entity to move CO2 from Japan to Malaysia primarily. On the technical development, these are the different sizes of ships that we are capable to move CO2, right from the small ones of 7,500 all the way to large 96,000 or 100,000 ships. What is also interesting is CO2 right now is considered a waste product, and CCS is moving of CO2 for waste disposal. But there are alternate ways of dual cargo ships where you can transport CO2 one way and on the return carry methanol or other cargoes like ammonia. CO2 is a little different from the other liquefied gases from shipping point of view. And on the table on the left, you can see the low pressure, medium pressure, and elevated pressure. The graph on the right shows the pressure temperature curve, and CO2 has a unique property of the triple point. The triple point is the point where the red, blue, and the black lines all meet. That's when the phase change is possible from solid to gas, gas to solid, and also in liquid. It can exist in all the three phases. So for the transportation of CO2 by ship, the ideal way is to keep it in the liquid phase. For liquid phases, there are three different regimes right now being explored. Medium pressure, this is tried and tested. Ships have been operating for more than 35 years, moving CO2, primarily for the food and beverage industry, but the same specifications are used for the Northern Light ships. Low pressure, where the temperature is lower to -50. These are being explored primarily for the APAC region to move larger volumes of CO2. The third one is elevated pressure, which is another alternative. However, it does have a lot of technical challenges. It is not as mature. The TRL is a little lower compared to MP and LP. One unique property of CO2 is the density, the liquid density. This changes with the change in temperature, and it is sufficiently pronounced to involve fair amount of technical work to handle the higher density, especially in low pressure. Coming for ships itself, CO2 is transported in what is called Type C tanks, which are independent pressure vessel types. There are quite a few different designs. As you can see, I've had quite a bit of spare time to make all these in PowerPoint. You have the typical cylinder type where you have spherical or cylinder shape. You have conical, you have the bilobe tanks, and then you have the trilobes. On the ship sizes, the blue one is following the medium pressure. So you can go all the way up to about 20,000. But from 12,000, 20,000 and going larger, you definitely need low pressure ships. One of the main constraints is the thickness of the tank. There are limitations to how thick the tanks can be. and that defines whether we can go for larger ships or not. A very quick rough calculation for India. If India wants to move, for example, 500,000 tons of CO2 from the east coast to the west coast for injection in the greater Bombay area, we would need one 20,000 ship, or two 12,000 ships, or three 7,500 ships. This is a very rough number. Further detailed studies needed from the exact location till destination. So India can actually work with medium pressure, which is an existing tried and tested technology. We have ships operating with medium pressure for more than 35 years. Another area which is an advantage to India are the three main components for shipbuilding. You need to have the shipyards which can build ships. Cochin Shipyard is a very good example. You need tank manufacturers to build the these Type C tanks. There's a fair amount of experience within India where you have manufacturers manufacturing Type C tanks for other areas and other industries, specifically for CO2. And the last one is steel manufacturers. I think we all know that most of the large steel plants are all based in India. Development of steel for the transportation of CO2 is not something new, at least in India. So with the main three components all present, Make in India is also a possibility for the ships. As for a track record, MOL holds 25% in a company called Lavik Shipping, and they have been moving CO2 for the last 35 years for the food and beverage industry. Most of the beer and aerated drinks and Coca-Cola in Europe are all manufactured using Lavik ships, CO2 which is transported. The picture on the top right is Lavik ships discharging at the Northern Lights for the initial commissioning phase. The project in the bottom right, the picture is a ship called the X-Cool, which is a demonstration ship by the Japanese government to demonstrate the use of low pressure and medium pressure. While low pressure is not really relevant for India, medium pressure is existing technology. There are various permutation and combinations for moving of CO2, and what I'd like to highlight a couple of options which could be relevant for India in the future. So while you have the initial phase of capture until the initial temporary storage, should you need to move CO2 from the capture plant? So for example, ArcelorMittal Nippon Steel is building a huge steel manufacturing plant near Vizag. And if we want to move that CO2, for example, to the west coast, you could use ships. The one option is we discharge the CO2 on shore, for example, in Mumbai, and then via pipeline, it is transported till the rig, converted into dense phase and injected. The other options are more marine solutions, where you can have directly ship to platform transfer, or ship direct injection, or ship to an offloading floating storage. So there are various combinations. Depending on the project demands, we can accordingly customize the necessity. From an economic viability point of view, for CCUS to be actually economically feasible, the price of carbon needs to be higher than the price of CCS. Otherwise, it doesn't give any economic incentive to companies to do CCS. So one of the main drivers is policy from the government. And until the policy and until the price are sufficient, the governments would need to subsidize either by subsidies, grants, or bearing some of the cost for difference prices. The graph on the top right shows the price of CO2 in Europe under the EU ETS, and this price is roughly about $80 to $95, whereas actual CO2 or CCS, the full value chain, is roughly about $150. So that difference would need to be paid by the governments as part of subsidies. There are some technical challenges with transporting CO2, and one of the big ones is impurities. So CO2 is normally transported in near pure form, and the purity of CO2 is not of that much relevance. It is actually the impurities which is of bigger importance. Now, when CO2 is captured from different industries, be it steel, be it power, be it cement, the captured CO2 results in different impurities. Let's assume we work with 99% pure CO2. The remaining 1% impurities can have different compositions. And mixing CO2 between a steel industry and a cement industry results in those impurities interacting, causing various side effects, if you want to call it. A very high level indicated in the hexagon, I've indicated some of the different results, like you have corrosion risk, you have toxicity, acid formation, acid dropout, are all very important concerns. Northern Lights, which is one of the most advanced CCS projects using marine solution, has revised the specifications of the CO2 already thrice from the time the initial project specifications was issued in 22 to the more recent June 2025 specifications, where they have progressively tightened the specifications of the impurities. So it's not the purity, it's actually the impurities which is of more importance, and a fair amount of research would need to be done in India with the different capture technologies used for different industries and what happens when you aggregate the CO2. Another concern is vapor return, but I won't go too much into detail in this because of time constraints. CO2 solutions, CO2 shipping can be used for both CCS and CCU. So even if you have a utilization plant, you can use CO2 shipping to move the CO2 for utilization. Thank you very much.
Thank you, Mr. Sony. Our next speaker is Dr. Thomas Koller, Regional Hydrogen and CCUS Segment Lead, APAC. Dr. Thomas.
Good morning, everyone. As introduced, I'm Thomas Koller, and I'm the Regional CCUS Segment Lead for APAC for DNV. Many thanks for joining us today. Thanks for my fellow panelists for the invitation into DMG. Great to be part of the panel today. DNV is a global assurance and risk management company. In our energy business, we work to provide assurance on energy infrastructure through the full value chain, from concept, from financing of projects, initial design, through to the building and the commissioning of projects. And this includes for carbon capture and storage projects, where we can advise, verify and certify from capture, transport and storage elements of that value chain. DNV has laboratories and test sites around the world, and at these sites we have capabilities to test and conduct experiments in the field of CO2. The pictures on the screen here are from recent experiments we've done at our facility in the UK. The picture in the bottom right you can see is a CO2 dispersion from an experiment we did to understand the consequences of a CO2 pipeline rupture. And the other photographs are from hydrogen-related experiments we've done to test the consequences of hydrogen. So we're actively involved in providing the foundational research to support the emergence of CCUS projects around the world. Turning to India's CCS opportunity, India's pathway to net zero by 2070 will require a portfolio approach, accelerating renewables and electrification, improving energy efficiency, and deploying CCUS in hard-to-abate sectors. And this includes cement, iron and steel, refining, chemicals, and certain power applications. The chart on the screen here that you can see is taken from DNV's Energy Transition Outlook research. This shows CO2 emissions over the next few decades for India, Bangladesh, and Sri Lanka. And you can see that due to renewables progressively replacing and displacing coal, particularly in the 2030s, there's a clear peak and decline in greenhouse gas emissions from power generation. But what you can also see is that emissions in the manufacturing sectors are stubbornly not coming down. And this is where the case for CCS is strongest. in terms of capturing emissions resulting from manufacturing processes. Across India, as we've heard from the panelists today, India has very promising geological assessments. There's very promising theoretical storage. And this is across multiple basins, and this, in theory, provides a physical basis for durable and permanent CO2 sequestration. What I want to discuss today is some of the lessons that can be learned from international projects that have successfully stored CO2 underground. And what I want to show is how learning from these projects can help take advantage of the CO2 storage need that India has and the CO2 storage potential that India has. And my hope is that this helps inform the policy framework that's being developed by the Indian government to support the emergence of CCUS. CCUS is developing globally, progressing from initial projects into larger hubs. And this has created a library, a very accessible library of technical information, commercial information, regulatory and social lessons that can be adapted to India's context. So a first lesson that can be learned that can help advance India's own CCS ecosystem comes from Sleipner. This is the world's first industrial-scale CCS project in Norway. This taught us the lesson that CO2 storage in aquifers is safe and that it can permanently store CO2. It also taught us about the importance of seismic monitoring to demonstrate CO2 migration. And many regulatory regimes around the world have looked at this project and learned from this project and put in place, enshrined a really robust monitoring practice, and that's important. The CarbonNet project in Australia also has lessons that others can learn. And I think there's lessons here on the commercial side, on business models, and on regulatory challenges. A key lesson that we can take from CarbonNet is to focus on storage first. So the philosophy behind the CarbonNet project is to put the transport and storage infrastructure in place and then let different CO2 sources come to them. And this is expected, in the Australia case, this is expected to be CO2 coming from coal power plants and CO2 emissions that are coming as a result of fertilizers, synthetic fuels, even hydrogen that's being produced in Victoria and the wider Australian continent. CarbonNet is funded by the Victorian government and the Australian federal government. And on commencing, it needed to put in place a procurement model to support the outsourcing of particular scopes to technical consultants. It needed to suitably distance itself from the regulatory part of the government, and it needed to build its own expert teams. That all took time. Another lesson is to have clear roles and responsibilities for public organizations, for private organizations that will need to collaborate to make these projects a success. And this includes clear roles and responsibilities for different public bodies that might be involved. In the CarbonNet example, this project took 9 years to resolve how state and federal regulators would work together and what each of them would manage. Starting operation last year, many in the room will have heard of Northern Lights, and it's been referenced today. It's certainly a leading project around the world that we can take lessons from. This is the first cross-border open market and open source transport and storage network, a huge achievement for the CCUS industry worldwide. Building this end-to-end value chain, again, has lessons for other projects and other countries that are developing the CCS ecosystem. As we heard, the CO2 stream composition, it needed to be able to handle CO2 coming from different emitters, from different sources. And CO2 specifications had to be written and agreed upon by different participants but written in a way that future participants would be able to access. And DNV led the task force to write the liquid CO2 specification relevant for receiving CO2 infrastructure. This ensures that different emitters, but also the downstream transport and storage, then can have confidence in the materials that's required to transport and store that CO2, and that these assets can be operated in a way that's in accordance with health, safety, and environmental principles. Another specification was required for ships, for the jetty, so we have the CO2 cargo quality specifications and updated international ship and shore interface standards. I mention these because a lot of these standards are in the public domain. They can provide the starting point for other projects around the world. Business models are also developed, and again, there are NDAs, there are technical information sheets available for would-be participants in the Northern Lights project, but that can be instrumental in shaping projects elsewhere in the world. There are heads of terms available. There's a fully termed transport and storage agreement that's available. These don't need to be reinvented. A final lesson that I take from Northern Lights is on the legal model. So for Northern Lights, the regulatory foundations are in place. This is based on EU legislation, and it's partly inspired by oil and gas regulations, but it remains untested. There have been no rulings, there's been no practice, there's scarce legal theory on this topic. And how the first instances or disputes that do arise, how those are handled, again, is a future lesson for other projects around the world. The final example I share is from the Quest project. This has recently celebrated its 10th year of operation. For this project, public engagement was really key, and this is the lesson I raise here. CCS was unknown to the local community, and there were questions and skepticism on whether public funding should go towards this project rather than other community priorities. So Shell and other project partners embarked on a program of community engagement starting years before the drilling commenced. NGOs were brought in to run town halls and share information, and active consultation with local inhabitants was done. And this helped inform where the pipeline that transported CO2, where that was placed in the local vicinity. This got people supporting the project. So there are important lessons for India in terms of engaging in the right way for the community relevant to the project. Build relationships over time and to the right level, no less and no more. So from Northern Lights and other leading international projects, we can identify some clear lessons that may help advance India's CCS deployment. Our first lesson is establishing storage certainty. First-of-a-kind projects in India should prioritize site characterization, certification readiness, and monitoring, reporting, and verification baselines. This is similar to what I identified in CarbonNet's approach. Establishing storage certainty enables multiple committers to connect over time, reducing counterparty risk, and helping on the economics and the cost side of things by bringing in more participants to share some of those costs of shared infrastructure. Related to this is the importance of proven monitoring playbooks being used. Subsurface monitoring data should inform the approach to injection, how that's phased in over time. Should support how a storage project is looking to ramp up the capacity and also the contingency plans. A second lesson is to publish CO2 quality specifications. As I mentioned, Northern Lights has some that might be a useful starting point. Early specifications, early adoption of these really cuts risk, and there's going to be different participants in value chains covering temporary storage, ships, capture facilities, pipeline operators, onshore, offshore facilities. They all need to be adopting similar or shared standards. Where deviations are needed, require documented equivalence. Be clear and upfront on what that equivalence must look like. A third lesson is to decouple capture and transport and storage risks. Treat capture, transport and storage as separate but interoperable investment lanes. This is going to attract different capital pools to the different parts of CCS value chains. And this helps appreciate the different risk for those different parts of the value chain. Different policy support may be required for those different parts of the value chain. So again, decoupling is a suitable approach to take. For industrial capture, relevant to the Indian market, anchor revenues can combine storage service fees, carbon crediting, a compliance value. You could pair electricity sales with CCUS uplift instruments like contracts for difference, for example, or tax credits. On the storage and transport side of things, you might want to consider a usage fee model, availability commitments, or something like a regulated asset base to help lower the weighted average cost of capital. A fourth lesson is on enabling early regulation. A project I didn't mention, but another lighthouse project is Gorgon in Australia. This is a really good example of the importance of putting legislation in place years before you want the project to begin to store CO2. The Western Australian government put in place environmental and indemnification provisions into legislation more than 10 years before CO2 was stored in Western Australia. So again, India can learn from this project and front load enabling rules for CO2, storage licensing, site certification, and long-term liability transfer. Having certainty on these and other important aspects is vital for investment coming into CCS. And the last lesson is on social licensing and stakeholder engagement. Engage early and continuously. So to conclude, India can advance CCS deployment by leveraging global best practices. Reflecting on those lessons learned, how do we translate this for India? Well, costs, and particularly capture costs, remain a hurdle. Let's not ignore that. India can offset this, though, via targeted incentives and by prioritizing low-cost and high-purity CO2 sources for first-of-a-kind projects. On the transportation side, as we heard, there are ship-based CO2 logistics. These are emerging. Early Indian projects should, though, explore storage close to the emissions, then move to pipeline-ready corridors, and then later to near-shore, offshore storage. And start with one or two anchors, anchor clusters where emitters, storage, and supportive regulatory regimes and governments are all co-located. Then replicate this via standardized technology, standardized contracts, and standardized permitting processes. So my final word is that all of this really comes down to risk assurance and risk management. Bring the confidence to developers, bring the confidence to investors and to government. And this is what we're trying to do working on projects around the world. Thank you for your attention. Do connect with me afterwards if you'd like to learn more. Thanks.
Thank you, Dr. Koller. Now the last speaker is Pranay Sharma from NTPC.
Good morning, everyone. The topic is carbonated bricks, coherent called as C bricks, which utilize captured flue gas carbon dioxide to make carbonated fly ash building materials. Actually, when we started the carbon dioxide capture journey of NTPC, we initially started with methanol project, which has been shown by RedTech. Then we moved on to ethanol. DME can be always made from methanol, and sustainable aviation fuel, which we are going to make from ethanol. The project is under NIT. So on the left hand side is the fuel security of the India, and if you see the right hand side, top right hand side vertical urea, that project is also going to be rolled out. But the thing with these projects are, these are not actually carbon negative in nature. They do not sequester carbon dioxide, once you make methanol and ethanol, until again you are going to use it, burn it, and again the CO2 is going to be released. So when we did our journey, we did a lot of thought process. Then we thought there is another category of compounds in which the CO2 can be permanently sequestered. So we have actually two waste, one is fly ash and another is flue gas. So we had already set up a plant of 20 tons per day CO2 capture capacity demonstration plant of modest size at NTPC Vindhyachal. So we thought if we can sequester this carbon dioxide within the matrix of fly ash, then we will be able to generate a carbon negative building materials. So we did a lot of R&D. We collaborated with several institutes, CBRI, Indian Institute of Science, NITs, and this we did work over the past 3 to 4 years. Because our main aim is to roll out a full-scale demonstration plant. So we developed the process, and so this is actually, I'll come back to the process, just an intermittent slide for CO2 to methanol. So we already had this capability for CO2 capture on a large industrial scale and convert into a building material, into a fuel, liquid fuel. So what happened was, as I was discussing, we wanted to sequester carbon dioxide into fly ash. So we developed the process, and the patent is under the filing. And I'll tell you what is the process and what are the bricks. So if you consider bricks, bricks are of two types. One is traditional red clay bricks and another is the fly ash bricks. In the fly ash bricks, which are usually made at NTPC plants, those are of cement. So it has around 50 to 60% fly ash, 30% is sand, and the rest 10% is around cement. There is another category of bricks in Indian IS, which is fly ash lime bricks. There you have fly ash, and another component is lime. Where we innovated is we used lime as an additive with fly ash, and then we used CO2 both in the matrix as well as the curing system to generate a carbon negative material. If we see the difference between these three types of bricks, the cement content in red clay bricks is nil. Fly ash bricks is 8 to 10%, whereas in carbonated bricks it is nil. So our carbonated brick is absolutely cement free. Then you come to the CO2 sequestration, and CO2 sequestration is there only in carbonated bricks. It's around 5 to 7% by mass. Fly ash utilization is very high in carbonated bricks. It is around 90% by mass. The strength is more than fly ash brick. It is around 9.5 megapascal. And the manufacturing time is around 24 hours instead of 21 days in fly ash bricks and 3 to 7 days in your red clay bricks. So the real key differentiator, if you talk about the carbonated brick, is there is an actual CO2 sequestration really within a brick, and there is no cement consumption. The next thing is we have to roll out a plant. So plant capacity is actually 2 lakh bricks per day, which has been captured in the next slide. But the another thing is we have to sold the bricks, or there has to be a market for the bricks. So there are 3 things which we felt are most important. First is quality, which was 9.5 megapascal. Second is aesthetics. Aesthetics has to be pleasing, otherwise nobody is going to buy it. Third is the cost and codal compliances. So if we cover the cost as well as the codal compliances, then we will be able to really break through the technology. So coming to the codal compliance part first. Codal compliance for carbonated bricks is same as for fly ash bricks, because we only have fly ash, we have lime and carbon dioxide. Strength wise, we are matching more than 7.5 megapascal. Drying shrinkage is less than 0.05% as mentioned in IS. Moisture content is less than 20% as mentioned in IS. These are the mandatory codal compliances. Apart from this, there are certain other non-codal compliances, such as fly ash bricks are eco-friendly, but carbonated bricks, if you see, they are not only eco-friendly, but they offer a potential of carbon credits. They are carbon negative in nature. thermal insulation is better in comparison to the red clay bricks because fly ash is inherently present. Aesthetic appeal is grey. We tried several additives. We tried iron oxide. We wanted to make the brick red. We even went up to the extent of adding beetroot to it. But everything whatsoever we added now, because finally our process is like this, all those colors were leached out. So we decided not to, as well as the cost of adding an additive. Once you added iron oxide or we tried some nano-based additives, the cost became exorbitant. So we dropped the idea of adding the additives for color. So the key takeaway of this slide is carbonated bricks fulfill all the codal provisions. Now coming down to the main slide, how did we achieve this methodology of producing the carbonated bricks? See, we took fly ash and we took lime, and we took around 91% of fly ash and 3% of lime, and then we simply mixed it. So a dough-like material would be prepared. Then what we did was we added around 10 bar CO2 in a reactor, on a lab scale. Then we finally have rolled out, going to roll out the plant. What will happen is under the pressurized condition, CO2, see in Indian fly ash, the lime content is less than 1%. So there is no inherent potential of Indian fly ash to capture carbon dioxide. So we had to add lime as an additive, and then we added carbon dioxide at 10 bar. So once we added the carbon dioxide at 10 bar, any lime which is present in the brick would be immediately converted to calcium carbonate. So once it forms a calcium carbonate, then that material we tried to press and form a brick. But it didn't give any strength because all the lime was converted to calcium carbonate, but there was no free lime present which could give the strength. So we could obtain the carbon negative brick, but strength was not there. So what we did was, we took an attrition mixture, the dough-like material which was produced, we further attritioned it, and now we added an additional 6% lime quantity. That lime is free lime. So within this free lime, so this would be now responsible for giving the strength. Thereafter we took a brick press of 50 ton load per brick, and we pressed the brick. And once the brick was pressed, and then finally we pre-cured this brick using the steam. We have enough steam in power plant. So we took the steam and pre-cured it, and then this whole brick was moved on to an autoclave. So in autoclave we took the steam from power plant at around 10 bar and pressure 10 bar, and steam is around 190 degrees centigrade. And using that steam curing, we could produce the brick which was 7.5 megapascal. Another point to note is in the reactor when we are adding CO2, we are only reacting with the matrix of fly ash. So another innovation we did was, after autoclaving, the steam curing of brick, we also subjected the brick to a CO2 curing at 10 bar in the extreme right hand side. So what happened was, not only the matrix CO2 is reacting, but also on the surface CO2 is reacting. And finally we got the brick was of around 9.5 megapascal. So our key innovation, if you consider this whole process, there are two key innovations. First is reactor. In the reactor we are reacting CO2 at 8 to 10 bar with fly ash to convert not only lime but also the calcium oxide present within the fly ash to calcium carbonate. And another is then that is basically responsible for carbonation, and another is we add again lime and then we surface cure it to further do the carbonation. So finally we had to roll out the plant. So we did a lot of trials, and also once you do carbon dioxide surface curing, we believe that most of the carbon dioxide won't be on surface, only how much there is carbon dioxide within the center of the brick. So we did all the thermogravimetric analysis and STAs and everything, and we found that when we have 3% lime in the first stage and 5% lime in the second stage, the strength was 9.7 megapascal. Average surface carbon dioxide was 7.5%, and within the center it was around 6.5%. So as we increase the lime, the percentage CO2 is going to increase. See, it's like simple, it's like preparing a tea. The more sugar you add, the sweeter the tea will be. But at the same time, we have to see the price. Just a tea cannot be too sweet, so it will create diabetes. So our lime should not be too much that it crosses the break-even point. So what we finalized is, if we go to 5% lime, we achieve around 8% to 9% CO2 capture in the brick. So what recipe we finalized finally in the process was to have 3% in the first step and 6% in the second step. Actual strength we obtained was 10.2 megapascal, but we wanted to be safe and we have said the brick strength would be 9.7 megapascal. So overall the building blocks of the plant would be like this. For CO2 capture, there would be a 50 TPD CO2 capture from flue gas based upon tertiary amine. Then there would be compression and storage of CO2. This would be building block 1 because CO2 has to be stored at a certain pressure. Then only it can be pumped into the fly ash matrix. Otherwise in the gas phase it would be very difficult. Then building block 2 is addition of fly ash, 3% lime. Then CO2 in the carbonation mixture, then addition of lime, then brick press, then steam curing, and finally CO2 curing of the brick. So these were the utilities which we identified. The land requirement was for CO2 capture 0.25 acre. For carbonated brick, total 5 acre, including the plant and stockyard. Steam requirement was around 7 tons per hour, service water 13 tons per hour. Connected load is 1000 kilowatt. DM water is very minimal, required only for CO2 capture plant of around 0.5 tons per hour. So this was a site which we identified near Unit 4 Ramagundam, where JD plant is coming. So we would be able to get the CO2. So we rolled out the tender and the project has been awarded. And this would be the material requirement. Fly ash would be around 650 metric tons per day. Lime would be around 68 metric tons per day. Flue gas flow would be 15,000 Rm cube per day to produce CO2, which would be 99% pure. And 50 TPD would be the CO2 plant. So next thing was the costing. The main thing was the project has been awarded. So if you come out to the costing, we did the costing. 2 lakh is the capacity, 330 days, 25 years is the plant life. If we see the L1 bidder price, it was around 90 crore. And for the capex cost, for the installation services, it was around 36 CR. The total project cost is around 126 CR. And if we see the capex, it comes around to be 76 paisa per brick. Because it's an R&D project, so it came out to 76 paisa. But if we take all other factors, had it been purely commercial project, the capex cost would have been 1 rupees 91 paisa. Then we see the load. Connected load is 1000 kilowatt, but ours is a batch process, not a regular one, continuous. So our load requirement was around 500 kilowatt. Then we did the power costing, steam costing and everything. So the total O&M cost, so as well as O&M cost came out to be 0.45 paisa. If I take capex and 1 rupees 91 paisa, and if I add 45 paisa of O&M cost and OPEX cost of 2 rupees 56 paisa, so our brick cost comes out to be 4 rupees 48 based upon with financial costing, and 3 rupees around 3.5 rupees without financial cost, being an R&D project. So this is a product which is cost competitive from day one, and the numbers are based upon the actual awarded cost. So the project is under implementation, and it is been awarded last month, and we expect it to roll out within 18 months. So this is all from me. Thank you very much.
Thank you, Mr. Sharma. Thank you, ladies and gentlemen. It was a very interesting session. I personally enjoyed it and learned a lot. I hope you also did it. Thank you very much.